Hello everyone, and in this segment, I'll show you the democratization of EM simulation. As Richard has already explained in his presentation about the EMC dashboard and a dashboard in a particular way. So this is the same. We will take another example. In this case, we will take example of the cable cross section, which is basic EMC EMC example. Yes. In this, I'll discuss about the dashboard where we can build the simulation processes and share them with our colleagues. So let's talk about the complexity of the simulation setup. As we already know that an electromagnetic simulation is very crucial part of many product design cycles, but it's not a trivial task to create a simulation setup. It requires extensive knowledge and experience of the field, and only an EMEG expert can set up these simulation and ensure that the results are accurate and reliable. So let's understand the need of an EMEG expert with an example. Let's say a design expert is designing the cable bundles and maybe their framework. Whenever they make any change in their design, they must contact an EMEG expert to verify their design for electromagnetic compatibility and immunity. Once the cable passed the test, then only the design can be finalized. So the question here is if it's possible to reduce the complexity of the process and find a way to get reliable results of the EM simulation without the involvement of EMAG expert. The answer to this is yes, and the solution is EMC dashboard, which can be easily created on the 3D Experience platform and can be accessed through any web browser. So in this presentation, I'll give you a brief about the EMC dashboard, why it is used and how it is used. We will start with the overview and the motivation. Then we will have a look at the example through which we will follow the entire process. I've taken a classic example of electromagnetic compatibility, which is the crosstalk between the cables. Then we will define the core of the dashboard by studying the effects of inputs like design parameters on the outputs in the design of experiment tool and create the approximation model. After this, we will discuss the challenges that we face during the approximation process and about the possible solutions that can be created. Next, I'll show you the implementation of this entire process in the Process Composer app. And in last, I'll give you a demo of the dashboard, which will conclude the entire summary of the dashboard. But before that, let me just introduce you to the CST and the platform we will be talking about in this presentation. We are familiar with CST Studio Suite. It is a high performance 3D electromagnetic analysis software package which is equipped with EM solvers for wide spectrum of application. It includes low frequency as well as high frequency, and in addition to that, it has some functionalities for thermal and structural simulations also. Whereas the 3D experience is a business platform which provides us clear and unified access to key services and apps. CST is one of those apps. Here we can collaborate with other apps, for example, the design apps, and can integrate the process and design and optimize our designs in a better way. So now let's have an overview of the process. In first step, a simulation expert sets up the simulation in CST. It is based upon the full simulation, which involves the meshing and the use of solvers. Then, in the next step, we will use the full simulation of the CST to create a relation between the input and the output. And on the basis of that, we will create a surrogate model. This approximation or the surrogate model will become the core of our EMC dashboard. User can now get the output from their inputs depending upon the approximation. And this also gives us an answer to our question why to use the dashboard. Now the designer has access to the simulation results without interacting with the EM tool, which is CST in our case. And also they can share the template and reuse the template provided that all the colleagues of there have the access to 3D experience platform. Here I have talked about the full simulation and the approximation. Both the processes have some pros and cons associated with them. In the full simulation, where we can ensure the accurate results and all the results will be available in the studio, but we need an EMAG expert to set up the simulation. Whereas in approximation, we will get the results very fast, but we the results may not be highly accurate, not always highly accurate, sometimes they will be accurate. So because they are based upon the approximation. And also the DOE that I talked about, the design of experiment can only handle zero dimensional data, which means 1 point data. I'll talk more about it in the later slides, and this is going to serve as a challenge for us in the optimization process. So I'll show you how it is a challenge and how we can work around this. But for now, let's just remember that the first process is to create a CST full simulation, then to use the data of the CST and the CST simulation to create a input output relation and create the surrogate model. Then on the basis of that, we can create a approximation which we can use in our EMC dashboard. Now we have taken a very basic EMC problem where we are studying the effect of an aggressor cable on the victim cable which is lying in its vicinity. We are varying the length of the aggressor cable which has been excited with 1 volt of voltage from one end, and a variable load is applied to the another end of the aggressor cable. Both the ends of the victim cable has been terminated with some load, and we are not changing it for this case. So whenever a wire is placed near an active wire, the voltage and currents are induced in this wire due to the electromagnetic fields that we can check in the results. As you can see, there is induced voltage in the on the both ends of the victim wire. We are interested in the maximum voltage induced at, let's say, one end of the victim cable and the frequency at which this maximum voltage is occurring. For that, we have defined the output variables in the post-processing, which returns the maximum value of the given curve. So the next step would be the DOE, which is design of experiment setup and the approximation. In the optimization process composer app of 3D Experience platform, it offers us design exploration tools where we can use the design of experiment tool to study the effect of all the inputs like the aggressor length, separation, aggressor load on the output of our model. Here we use the CST model and create a loop where with each run, a set of input is applied to the model and we get a set of output corresponding to that set of input. Now we have the collection of input output data, right? So this we can analyze in the result analytics app, where we can explore all these data sets and create the surrogate models to visualize the behavior of the data. And this will help us to predict the new value of the output parameters based on a combination of value of input parameters where that combination does not already exist in the dataset. Both these processes will act as the black box for our EMC dashboard, where the user can feed the input and get the output without worrying about what's going inside the black box. So there are some approximation methods on the basis of which the surrogate model is created. In the result analytics app where we create the approximation, there are 4 approximation method at present. The first one is the radial basis function, which is based upon the neural network. It has a short initialization time and it is mostly preferred when all the inputs are independent of each other and are of equal importance. The second one is the response surface model, which uses a polynomial combination of vectors representing the input parameters. The order of the polynomial regression model depends upon the number of data inputs in the dataset. It is only valid for simple smooth functions and it won't be valid for, let's say, a non-linear function. The next one we have is the universal Kriging method, which converts the partial observation of a spatial field and use it to the prediction of that field at unobserved location. And it creates a very good approximation in the cases when our data inputs are in very small units, let's say 100. And it may not give us good results for 1000 or more than that. The last one is the latent variable Gaussian progress regression method. It is supervised learning method, and it is very much similar to the universal kriging method. It is the extension of the Gaussian process regression method. The thing that makes it different from the universal kriging is that it can handle numerical as well as non-numerical data, which includes strings. In this project, we have taken radial basis function uh, for our project, and that's why I'll explain more about it in the next slide. So let's understand the radial basis function with the help of the example that we have taken of the cable cross section. Let's say we have two inputs, which in our case is aggressor length and the separation between the two wires. And they are acting as Xi and Yi. So corresponding to each of the input set, we will get the output, which will be the function of Xi and Yi. The idea here is to interpolate this function of Xi Yi to get a continuous approximation function of the complete design space. Now, due to this interpolation, we can predict new values of the output parameters based upon the specified combination of the inputs, and these inputs, the new inputs for which we have got the output, they are not present in our previous data set that we just had given to create the approximation. So the data sets are used to solve the linear equation, and from these linear equations we can calculate the value of approximation coefficient alpha. The approximation coefficient alpha along with the radial basis function constitutes the interpolation we are talking about here. The g of x here is the radial basis function. Now coming to the challenges that we faced. The DOE inside the process composer is designed to estimate zero-dimensional value, which means one-point data. But what we get in the CST is 1D curve for the induced voltage in the entire range from 0 to 200 megahertz, let's say. So we have to convert it to zero-dimensional data. One might think, if our desired parameter is only the maximum value of the voltage, which is a zero-dimensional data in itself, and DOE can handle that, then why it is a challenge? It's a challenge because for the accurate estimation of the maximum value of voltage, and in this case the spectrum's peak, the complete frequency range should be estimated and not just only the maximum value. And I'll explain why in the later slides. So in result analytics app, we can visualize the approximation in many easy ways. The image on the right shows how actual and the predicted data is related of an approximation of maximum value of the voltage. The green line indicates here the best approximation. Let me just highlight the, okay. So this is the green line and it indicates the best approximation. As you can see that the data points are close to the green line, it indicates that the actual and the predicted data are in very good agreement and the approximation is very good. But this is for the maximum voltage value. What about the frequency at which this maximum value is occurring? So the frequency of the maximum voltage, in case of the frequency, when we consider the frequency at which this maximum voltage is occurring, the results may not be highly accurate. The reason is the spectrum is limited and we are interested only in the maximum voltage. The frequency of the voltage can unexpectedly jump to the edge of the range, and this makes the frequency of the maximum voltage discontinuous. Due to this discontinuity, there is no trend to follow for the approximation and the results can be misleading. The approximation by radial basis function works best for the continuous values. So what do we do? How do we solve this problem? Well, I'll explain it with the help of one example. Let's understand the solution. So let's say we have a set of input parameters and let's say the length of the aggressor in our case is 450 millimeter. The termination that we have given to the aggressor wire is 25 ohms, and the separation between the victim and the aggressor wire is 15 millimeter. And we know that output parameter of interest here is the maximum value of the voltage at the victim cable and the frequency at which this maximum value is occurring. So if we directly estimate the maximum value, we get a 1 point approximation, which can be seen with which is here indicated by this green dot. If we compare this maximum value with the one we get from the simulated results, the difference is huge. As you can see, the maximum value from the simulation is somewhere here, and the 1 point approximation is giving us value somewhere here. So we figured the best way is to approximate the entire frequency spectrum first, then interpolate the data, and then obtain the maximum point. It gives us far better results. Let's see how. So here, the orange curve is the approximated spectrum. And when we, in this case, when we calculate the maximum value of the voltage and the frequency, we can see the simulation and the approximation results are in very good agreement, whereas this 1 point approximation is still far away. And the same can be verified from this table, where we can see the simulated one is at 35.5 megahertz. The approximation with the 100 points which we have taken here is at around 38 megahertz, whereas the 1 point approximation is giving us the results at around 84.34 megahertz, which is a huge difference. So from here, we can conclude that instead of getting 1 point approximation, we need to approximate the entire spectrum, interpolate the data, and then only obtain the maximum point. But our DOE can handle only zero-dimensional data. Then how do we approximate the entire range? So we have extended the simulation workflow of DOE to handle 1D signal by the Python script. Now we are resampling the range in 100 samples. Here I'm taking the 100 sample as an example, let's say. So we are resampling the range in 100 samples, and each sample is assigned as an output variable in the script. So instead of calculating one zero-dimensional output, now the DOE is calculating 100 zero-dimensional outputs. Later, we are interpolating the data with the help of approximation models and then creating a surrogate model. Once we get the data of 100 samples in the result analytics app under the guided analytics, we can create a new approximation. And here we have used the radial basis function as our approximation method. And once the approximation coefficient data is ready, which is indicated here. So once, I'm so sorry, I'll just a second, I have, okay, yes. So once it is created and it is ready, we can export the data from the result analytics app, and we can use this exported data later. In the next step in optimization process composer app, we run two activities. One is the approximation, for which we have used the approximation coefficient data that we just exported from the result analytics. We import it here, do the interpolation, and get the maximum value of voltage and associated frequency. This is based upon the approximation model. In other activity, we are directly running the CST and getting the simulated results of the maximum value of voltage and the associated frequency. A switch is used to select which activity to run. This process will be more clear if I show you the demonstration. So let's move to the demonstration. Okay, so whenever we create any process in the process composer, we can take that data into the process experience studio, where we can create a very nice GUI out of it. When it is created, we can share the same with our colleagues. Here I have shared it with myself just to demonstrate. And once it is shared, so once it is shared, the other person can open the same in the performance study app, where all the data that we had given in the process experience studio is now available in the performance study, and it becomes a very user friendly GUI. Let's have a look at what we have here. So we have an image of the aggressor length, victim length, and the separation between the two wires, just to showcase what our application is about. Next, we can provide the inputs. In our case, we are taking three inputs, which is the length of the aggressor, separation between the cables, and the termination with which we have given to the aggressor wire. We are varying the values uh, between some values, and then we have given a checkbox which is for the CST simulation. So whenever we are enabling this option, we are running the CST simulation alone, and whenever we disable it, we are running the approximation only. On the basis of this, we have 1 point approximation data. This is the output that we will get from the simulation, and then we have 100 sample approximation, and then the simulated data which we are getting from the CST. Same, we can get the simulated and the approximated spectrum each time when we run the simulation. So let's say we give some input. Let's change the input to let's change the input of the length of the aggressor wire to 350 millimeter, the separation between the wire to 15 millimeter, and let's keep the aggressor termination with 30 ohm load. And for this, we are only running the approximation and not the CST. Once all the data is saved, we can run the simulation. And as you can see, the 1 point approximation and the 100 sample approximation results has been updated. Now, to check whether this result is in agreement or not, in agreement with CST simulation or not, we will run the CST simulation. For that, we have checked the CST simulation. Once all the changes are saved, we can run the simulation. And once it is done, now we can check and compare the results. So for the CST simulated results and 100 sample approximation results are in very good agreement, whereas this 1 point approximation result is giving us very different results. So once the CST simulation is completed, the simulated spectrum and the approximation spectrum also gets updated. Also, this simulated setup is also updated with the new inputs that we had given. We had changed the aggressor length, we had changed the separation between the two wires, which gets updated in this CST simulated setup. So this is the GUI, and as you can see, this is the dashboard, and it is very user friendly and can be easily used. So this brings me to the conclusion of what the process is that we have followed. We first set up the DOA in the process composer, and then we run it. Then we created the approximation model and from the result analytics app and exported the approximation coefficients from there. Then we set up the simulation process with needed functionality in the process composer, and then from there we took all that data to create a template in the process experience studio, which we later used in the performance study app to create the dashboard. Now this dashboard is ready to use and can be shared among the colleagues provided they have the access to 3D experience platform. So as I said in the beginning, now a design engineer does not have to depend upon an EMAG expert to every time to get the simulation right or to verify if their cable or any model that they have created um, is passing the EMC test or not. Now they can do it on their own, and the dependency on another person is reduced. So this reduced the complexity of the entire process that has been earlier followed. We have so this AMC dashboard is easy to use, can be shared, and we have used many applications here like the optimization process composer. Then we use the result analytics. I want to tell that this is only one example of the application for which the dashboard can be used, and such dashboard and all these apps can be used for a wide range of EMAG applications. So this includes the topic, and thank you so much.